When we deal with matrices, there are three things that we are allowed to do to a matrix that doesn't really change it. It just writes it in a different form. And we call those elementary row operations. So we are allowed to interchange two rows. That doesn't change the problem. We're allowed to multiply a row by a non-zero constant. So if I want to take one of the rows and multiply them all by 5, I can do that. And I can add a multiple of a row to another row. That's a more complicated one, but those are all things that don't really change the problem. So on number 3, we want to identify the row operation being performed. Okay, so hopefully you can see that this first row did not change. 102 didn't change, and the third row didn't change to negative 614. Okay, so those two rows didn't change. What did change was this middle row. So we need to figure out what happened. Well, did we interchange two rows? And well, clearly we did not, because the other two are the same. Did we multiply this row by a non-zero constant and get those numbers? And no, we didn't, because I don't know what you would multiply 3 by to get 0 other than 0. So we didn't do that. So what we must have done is we must have added a multiple of one row to another row. So let's see. Maybe this. If we multiply this row by negative 3 and then add it to the second row, what happens? Negative 3 times 1 is negative 3 plus 3 would give us 0. Negative 3 times 0 is 0 plus 1 would be 1. And negative 3 times 2 is negative 6 plus 7 would be 1. So that's what happened. We took row 1 and multiplied it by negative 3 and added it to row 2. Okay, so that's an elementary row operation that was performed there to get this new matrix. These matrices are kind of equivalent. I know they don't look the same, but they are equivalent as far as the equations. Now, we have something called row echelon form and reduced row echelon form. So row echelon form, there's three things that are required. Any rows that are entirely 0 at the bottom. All other rows have 1 as a leading coefficient. And the leading one in each row is further to the left than the leading one in a lower row. Then one step further than that is called reduced row echelon form. And that is when every column that has a leading one has zeros in every position above and below its leading coefficient. So for the next three matrices, we want to decide if they are in row echelon form and if they are in reduced row echelon form. Okay, so let's look at this first one. First requirement, any rows that are entirely 0 at the bottom. Oh, we don't have that, so ignore that. All other rows have 1 as a leading coefficient. So there's 1, that's the leading coefficient. This is the leading coefficient, and it is not 1. So this is not in row echelon form. So it's not going to be in reduced row echelon form. Okay, let's check the next one. Any rows that are entirely 0, we don't have any that are entirely 0. All other rows have a 1 as a leading coefficient. So my first number in this row is 1. My first number in this row is 1, 1, and 1. So that's good. The leading one in each row is further to the left than the leading one in a lower row. That's true. Do you see how these stair step down? So that's good. So this is in row echelon form. It met all of the requirements. Now we want to see if it's in reduced row echelon. Every column that has a leading 1 has zeros everywhere else. So we're looking at this leading one, all the rest zeros. So far, so good. This leading one, all the rest zeros. This leading one, that is not a 0. So this is not in reduced row echelon form. It's in row echelon form. Okay, last one. We're going to go through our checklist. All rows that are entirely 0 at the bottom of the matrix. Yes. All other rows have 1 as a leading coefficient. Yes. The leading one in each row is further to the left. Yes, they stair step down. And every row with a leading coefficient of 1 has zeros everywhere else. Those are all zeros. Those are all zeros. Yes. So this one is in reduced row echelon form.